Ever since the childhood, we are familiar that a stone thrown upwards falls back on the earth. A fruit from the tree falls down. The motion of planets and stars. All these and many similar activities are the result of gravitational effect of Earth. Gravitation or gravity is a natural phenomena by which all the things with mass or energy are brought towards one another. On Earth, it gives weight to physical objects, and the moon's gravity causes ocean tides. Initially, it was studied by Galileo and further Isaac Newton discovered that the gravitation is a universal property. Let us consider the fundamental forces or the interaction between matter. The first interaction is gravitational interaction. This is because of the two objects or bodies having a huge mass. There exists a force of attraction between two such material bodies known as the gravitational force. If we consider the charged particles subjected to a electromagnetic interaction or electric and magnetic field, these are called as electromagnetic interactions, and the forces acting on these charged particles are called as electromagnetic forces. There also exist interactions between nuclear particles like electron, proton and neutron. But these forces exist over certain distance, which is called as the equilibrium distance. If the distance is less than the equilibrium distance, the force of attraction between the two charged particles are very strong. Therefore, these are also called as strong interaction. At the same time, if the distance between the two nuclear particles are more than the equilibrium distance, these forces are very weak. Now let us see the important characteristics of the gravitational forces. Among these, the gravitational forces are the weakest, has no significance at subatomic level, but it is the dominant force at macroscopic scale. It is responsible for holding the earth together and retaining on it the atmosphere. Holding the earth together and retaining on it the atmosphere. Binding the earth and the other planets to the sun, or binding the stars together into the galaxies, etc. So, the gravitational force is the cause of formation, shape and trajectory of the astronomical bodies. The scientist Copernicus gave his heliocentric theory in 1543, and he suggested that the sun is at the center of planetary system and planets are moving around the sun in a closed orbits. Then the scientist Ptolemy in 2000 years ago proposed a geocentric theory. In this theory, it was assumed that the earth is at the center and stars, planets, sun moves around the earth. The Tycho Brahe made the clear observations for the motion of planets around the sun, and he collected the huge data related with the planetary motion. The Kepler used this data and he gave 3 laws of planetary motion. In 1666, Newton derived his universal law of gravitation from the Keplars Laws of motion. So this is the brief history of the theory of gravitation. The Newton was explaining and also examining the motion of objects in space. Armed with the knowledge of the Kepler and Galileo, he developed a comprehensive model of universe. This model is now referred to as the law of universal gravitation. Now, Newton found that the apple falls on the surface of the earth. It comes down towards the earth. At the same time, he finds that if we consider the earth and the moon is revolving around the earth continuously, but it never fly off at the tangent to this circular or path of its motion around the earth. And from this, Newton concluded that there must be some force of attraction which binds the earth with the moon, and he called this force as gravitational force or gravity. So from this he concluded that there exists a force of attraction between two material bodies. He called this force as force of gravitation or gravity. Now, from the data of Tycho Brahe, by careful observation or study, Newton found that the force existing between these two material bodies is a function of square of the distance, or this force is inversely proportional to the square of the distance, which is nothing but the inverse square law. Also, he found that this force is proportional to the product of the masses of the two material objects. That is, F is proportional to m1 and m2. Or we write F is equal to z into m1 m2 upon r square. This constant g is called the gravitational constant. Now we can state the Newton's law of gravitation as every particle in the universe attracts every other particle with a force that is proportional to the product of their masses and inversely proportional to the square of the distance between them. And this force is always acting along the line joining the two particles. Such forces are called as central forces. Or we write this gravitational law of Newton as F is equal to gm1 m2 upon r square. The value of this gravitational constant is found by Henry Cavendish in 1798, which is found to be 6.67 into 10 to minus 11 Newton meter square per kg square. Unlike Kepler's constant, this constant is a true universal constant and applies to all bodies in our universe, from protons to black holes. Now, in order to get idea about the magnitude of this force, gravitational force, let us consider two examples. The first example, two young lovers, a boy of mass of 60 kg and a girl of mass of 45 kg are sitting 1.2 meter apart on a park bench. They feel a mutual attraction towards each other. Now we calculate what is the magnitude of the force by using Newton's law of gravitation. F is equal to gm1 m2 upon r square. By substituting all the values, we find that this force comes out to be 1.2506 into 10 to minus 7 Newton. So the magnitude of this force is very small. Let us consider another example. We calculate the force of attraction between two large super tankers, each having a mass of 2.3 into 10 to 7 kg, moved 124 meter apart. Again, by using Newton's law of gravitation and substituting the values, we find that this force again comes out to be 2.3 Newton. So even though we are considering the huge mass 2.3 into 10 to 7 kg, still the magnitude of this force is 2.3 Newton. So this is still a very small force. So we see that the force of gravity is the weakest of the four basic forces which we have seen at the beginning of this topic. So these forces are negligible. Now let us consider the Kepler's laws of planetary motion. Kepler was a mathematician and astronomer interested in how the planets moved in the night sky. After collecting numerous amount of data about the motion of the known planets, he came with up three well-known laws of planetary motion known as the Kepler's laws of planetary motion. Let us consider the Kepler's first law, which is also known as the law of elliptical orbits, which states that all the planets move in the elliptical orbits and the sun is situated at one of the foci of the ellipse. So the path followed by the planets is not circular, but it is elliptical. Then we consider Kepler's second law, which is also known as the law of areas and can be stated as the line joining the planet to the sun sweeps out equal areas in equal time as the planet travels around the ellipse. That is, the aerial velocity of the planet is constant. From this figure we see that here we have the sun and the planet which is moving in an elliptical orbit. So when the planet is far away from the sun, its velocity is lower because here the radius of the orbit is more. So if we calculate the area, shaded area here, and if we consider this another situation, that is when the planet is nearer to the sun, then here we find that the radius is smaller. So in order to keep the area constant, it has to move faster. So in short, we see that the planets move slowly when they are far away from the sun, and they move faster when they are nearer to the sun, so that the area swept out in a known time interval remains constant. Now let us consider Kepler's third law of motion, which is called as law of periods and stated as the square of the time period of the revolution of the planet is proportional to the cube of the semi-major axis of the ellipse traced out by the planet. This is known as harmonic law and written as t square is proportional to u. This law has very much importance. This can be explained by this example. Now we have to determine the period of the space station located at a distance of 6.6 into 10 raised to 6 meter above the Earth's center. If we know the radius of the Earth and the period of the Earth, so we write the relations r1 cube upon t1 square is equal to r2 cube upon t2 square. Here r1 is the radius of the Earth and t1 is the periodic time of the Earth. Here we have the radius of the orbit of the space station. Then we are interested to find out what is the periodic time of the space station. So if we solve this equation for T2, we find that the periodic time comes out to be 5300 seconds. So in this way, this third law can be used to determine the periodic time of any planet which is revolving around the sun. So friends, in this topic we have seen what we mean by gravity, what is Newton's law of gravitation and the Kepler's laws of motion. Thank you.